Hi, Assalamualaikum. We meet again in our class for chapter 2. Still discussion in part 1. Okay. Okay, let's continue our next topic. We have discussed this slide, part 1 of chapter 2, about the amplitude modulation in time domain. So let's now discuss about AM in a frequency domain. Okay, so the frequency domain provides an alternative description of the signal in which the time axis is replaced by frequency axis. So basically, for a sine wave signal, we have the signal is represented in terms of time domain, which is in the form of a sine wave time domain. This is this type of signal we can have when we are using oscilloscope. Okay, so the oscilloscope give us the signal in the time domain. So there is another way to represent the signal, which is in frequency domain. So frequency domain provides an alternative description of signal where the time axis is replaced by frequency axis. So the x-axis, the horizontal axis, is replaced by, instead of time t. So now we have f, frequency. Okay, but the vertical line or the vertical axis still presented the amplitude of the signal. So now we will discuss further about frequency domain. So we have this amplitude and frequency. So okay, the relationship between the time and frequency domain. So this is the signal, AM signal. Okay, so let's see this signal. First is okay, this is the first signal, modulating signal. Okay, first is modulating signal. Second is carrier signal. So you can see that this is modulating signal have low frequency, right? And this carrier signal have high frequency. So in terms of frequency, if you make the scale, so now you have at the lower part of the frequency axis, you have modulating signal. The frequency of modulating signal here. So here is FM. Okay. Okay, then the output from this modulation is, we call it the envelope. Okay, this is the envelope signal. So this envelope signal consists of several frequency. Okay, where you have we call it upper band. Okay, upper frequency, carrier frequency, and also lower frequency, lower sideband frequency. Okay, so this lower and upper frequency is close to carrier frequency compared to modulating frequency. Okay, so instead of time domain, we have the signal in terms of frequency domain. So you can see that here it has, in frequency domain, will represent the signal in terms of the amplitude, okay, peak amplitude and the frequency. So you can see that in this here you have this amplitude, the amplitude of the signal, the amplitude of carrier, here the amplitude, and also here the amplitude of lower signal. So in frequency domain, you represent the signal into these three lines: the amplitude and its frequency, the amplitude and its frequency, and the amplitude of lower sideband and its frequency. Actually, you have another one here, the amplitude, but far away below the amplitude and the frequency of modulating signal. Okay, so full carrier AM frequency domain. AM signal in time domain can be seen using oscilloscope. Okay, so time domain signal can be obtained using oscilloscope. So what is the machine or equipment that we can see the frequency domain? Frequency domain. What is the equipment? For frequency domain, we can use spectrum analyzer. So for the frequency, we're using equipment named spectrum analyzer, in order to display a AM signal in frequency domain. Frequency domain spectrum analyzer. Although both carrier and modulated signal is a sine wave, modulated signal is not a sine wave. If AM modulated signal is not a sine wave, then what it is? Okay. Full carrier. So this is given an equation. So this is the equation for AM signal. Okay. What is this? You have seen this in previous lesson. So this is the AM signal. Okay. So this EC is the magnitude of carrier. This is pressure index. This is omega M. Okay, this is omega C. So this signal consists of few component. We have omega here. We have frequency of carrier, frequency of modulating signal, modulation index, amplitude of carrier. So this signal we can expand. Expanding using trigonometric identities, this part, sine of sine. So the sine of sine. So you need trigonometry to solve this equation. So so this part, EC sine omega ct, this one, and this part, multiply here and here as well. So we got this sine of sine to be solved using trigonometry. Okay. Okay. So first term is the carrier, EC sine omega ct. So this is this is a very familiar equation. So this term is representing the carrier signal. But the second term can be expanded using trigono identity. So this second term need to be solved using trigonometry. Okay, from this trigono equation, sine A sine B equal to half cos A plus B, A minus B minus cos A plus B. So cos A equal to cos minus A to give this the expansion of this equation. This equation can expand this part. So this represent this part, second part of the signal. So this is still the carrier. Okay, so from that expansion, we got this, the carrier with omega c frequency, and we have MEC over 2 cos omega c minus omega m t. So this is called a lower sideband frequency. Okay, and this is cos omega c plus omega m, omega c plus omega m. This is called upper sideband frequency. So we take the frequency and magnitude, okay, from this equation to be plotted for the frequency domain signal. Okay, so the amplitude is for the first part, the amplitude is EC, okay, EC, and the frequency is omega c. Okay, change the color. Sorry. Okay, so the amplitude is C, the frequency is omega c. So this information we transfer to the frequency domain where we have the amplitude, which is omega c, and frequency omega c or fc. Okay, so the second part, which is the lower sideband, is we take the amplitude MEC over 2. So MEC over 2 here, and the frequency is omega c minus omega m, or divide by 2 pi, we got fc minus fm. This is the lower sideband. And another part of this equation is the upper sideband, where we have the same amplitude, MEC over 2, same, okay, but the frequency is omega c plus omega m, or fc plus fm. Okay, from this equation, this is the AM signal, AM modulated signal. So from this equation, we can summarize this equation into frequency domain representation, which is we only take the magnitude and frequency of this equation. So take this amplitude and plot into its frequency. The same goes for lower sideband and also upper sideband. Okay, so what are the sidebands? Sidebands or side frequencies are generated as part of the modulation process and occur in the frequency spectrum. So we call it side frequencies or sidebands are generated as part of modulation process. So when you modulate the signal, the outputs are in terms of sidebands. Okay, and it occurs in the frequency spectrum directly above and below carrier frequency. Above and below carrier frequency. So above carrier we call it upper sideband. Below carrier we call it lower sidebands. So sideband are single frequency sine wave modulation generate two sidebands. Okay, so if we modulate one modulating signal and one carrier signal, sine wave, the process will will give us two sideband, one upper and one lower. Okay, but complex wave, for example, the voice or video modulation process will generate a range of sidebands. Will generate more than two sideband. It will give you maybe 10 upper sideband and 10 lower sideband. Will give you range of sidebands. Okay. So we will, in this class we will consider only simple two sideband, lower sideband and upper sideband. Okay, so let's see this figure for AM signal. We have, this is the signal in frequency domain, where this is the amplitude. The Y is still the amplitude, but the x-axis is now the frequency. What is the unit for frequency? Frequency unit is hertz. Okay, if you have F, the unit is hertz, or if you have omega, then the unit is radian. Okay, so from here we have derived that the amplitude for this sideband, for the sidebands, lower and upper, the amplitude is EM over 2. What is EM? EM is the amplitude of modulating signal. Okay, so EM over 2, and the amplitude of FC is EC, right? So we have here EC and, okay, we will see later. Okay, so this is the block diagram for modulation, where we have, this is the input, the modulating signal, and this is the carrier, high frequency carrier. So the output is AM modulated signal. So this AM signal, if you see this is the signal shown using oscilloscope. Okay, this is the time domain. But if you tap the signal into equipment called function generator, the signal will be displayed in terms of frequency domain like this. Okay, so you have this signal time domain, and this is frequency domain. Okay, sideband in frequency domain. The figure, AM wave is algebraic sum of the carrier and upper and lower sideband sine wave. Okay, this one. The AN wave, or the envelope AM envelope signal is the algebraic sum of the carrier and upper and lower sideband wave. So here in this signal you have sum of carrier signal and upper signal and lower signal of the sine wave. Okay, so A is the modulating signal, this one A, very low frequency. B, lower sideband. C, carrier. D, upper sideband. And E, composite AN wave. Okay, so you can see that from this signal, it consists of 1, 2, 3 upper, carrier, and lower sideband. These instantaneous amplitude are added to produce this sum. So meaning that this one plus this one plus this one, you have this. So maybe some of you wonder where does this envelope come from, right? Why the signal become like this? So basically, in theory, the signal is the instantaneous amplitude sum or algebraic sum added together, and it becomes this envelope. Okay. Review question. Example, 1 megahertz carrier. So this is, what is this? This is the FC carrier with an amplitude of 1 volt peak. So this is EC, right? It's modulated by a 1 kilohertz signal. So what is this? This is FM, modulating frequency with M equal to 0.5. So M is the modulating index. Scatter voltage spectrum. Okay. Second, can try. So bandwidth. For a sine wave signal, you can discuss about bandwidth. Okay, signal bandwidth is an important characteristic of any modulation scheme. In general, a narrow bandwidth is desirable. If the spectrum space is limited, narrow bandwidth allow more signal to transmit simultaneously. Use narrower bandwidth will limit the spectral noise, thus increase signal to noise ratio (SNR). Bandwidth is calculated by, so for FM, so for AM signal, the bandwidth of AM signal is calculated by this equation B or BW equal to 2 FM. Okay, so bandwidth for AM signal, B equal to the bandwidth in hertz, FM is the modulating frequency, modulating signal frequency. Bandwidth is also the difference between the upper and lower sideband frequency. Okay, so we can also derive the equation for bandwidth in terms of sideband frequencies. So we can say that bandwidth is the difference between upper and lower side frequencies. So basically B equal to F upper minus F lower. So this is equal to 2 FM. The answer is same. Huh? Okay, sidebands in the frequency domain. A standard AM broadcast station is allowed to transmit modulating frequency. This is FM, 5 kHz. If the AM station is transmitting on a frequency of 980 kHz, so transmitting on frequency, this is the FC. Okay, FC. What are the sideband frequencies and total bandwidth? So sideband frequencies, of course, this is FC plus FM and FC minus FM. So what are the bandwidth? Bandwidth is 2 FM, 10 kilohertz. Okay, solution. Okay, you can read this. Example, solution, group activity, solution. Okay, you can read that on your own. Okay, homework, exercise, revision. Okay, revision, some revision. This is sine wave. So sine wave, V peak equal to V peak to peak multiplied by half. Okay, so V peak is V peak to peak. V peak is here. This is V peak. Okay, so V peak is V peak to peak multiplied by half. This is multiplied by 0.5. So V peak to peak divided by 2 is Vp. So this is Vp. Okay. Yeah. Vp is equal to VRMS multiplied by Z2. So VRMS equal to Vp divided by Z2, or 1.4. So if we have V peak divided by Z2, we get VRMS. Okay, so VRMS, you must remember, VRMS must be less than VP. Okay, VP equal to V average multiplied by pi over 2. So VP is V average multiplied by pi over 2. Okay. This is the revision for sine wave. Okay, power relationship. Power developed when carrier signal appear across the resistance R is P equal to, what is this? PC equal to AC over Z2 square. So what is this? AC over Z2? This one, right? This one. So PC is V RMS square over R. So rearrange the equation, we got AC square over 2R, because these two, so 2 multiplied by 2, so it become 2, this one. This part become this number. Okay, so AC square, the R remain, where AC is the peak carrier voltage and R is the resistance. Power relationship. The AM signal is a composite of the carrier and sideband signal voltage. Each signal produces power in the antenna. Total transmitted power is the sum of carrier power and power of the two sidebands. Okay, total power, because AM signal consists of 3 components, right? Carrier, upper, and lower sideband. So each signal, each of these, one, carrier, upper and lower, produce power in the antenna. So total transmitted power is the sum, is the total. Total transmitted power is the sum of carrier and sidebands of the signal. So PT equal to PC plus PUSB plus PLSB. Okay, so this is the equation. PC is PC AC square over 2R. We have discussed this just now. PUSB is EUSB square over 2R. PLSB is PELSB square over 2R. So for total become sum of these three. Okay. Discuss in your group, discuss with your friend how the power ratio can be further simplified into this. So how you can further simplify this equation, this one plus this one plus this one, become this equation. Power relationship sideband. The next step is to find power in each sideband. Two frequency components have same amplitude, thus they have equal power. Assuming sine wave modulation, each sideband is cosine wave where the peak amplitude is this one. Okay, so this is over 2, right? So the sidebands will appear across the same resistance R as the carrier. Lower sideband and upper sideband will have an equal power. Thus, total sidebands power will be m square over 2 multiplied by carrier power. Okay, so this is the equation. P LSB equal to ELSB over 2R. So ELSB is MEC square over 2 square. Okay. So at the end you get this PLSB equal to PUSB is equal to M square over 4 power carrier. Okay, so the total power in the whole signal is just the sum of the power in the carrier and sideband. So this is carrier power, and this is plus this one plus this one. So you can get this one. Basically PC plus a lower SB plus upper USB, upper sideband. So the total power become PC plus M square over 4 plus M square over 4. So when you simplify, you can get this equation. Okay. From that, we also can see the efficiency, transmission efficiency for AM. So the transmission efficiency is P sideband over P total multiplied by 100%, where PSB is the total sideband signal power that contains information. Using this equation, M square PC over 2 over total power, so equal to M square over 2 plus M square. If M equal to 1, 100% modulation, the average power PSB equal to 50%. PC equal to PC over 2. It shows that PSB is dependent on M. From this equation, we know that the PSB, okay, power at the sideband depending on the modulation index. Okay, therefore, given the equation of power of an AM waveform, the efficiency is M square over 2 plus M square multiplied by 100%. Can be seen from this equation that the efficiency of AM increases as the modulation index increases. So the efficiency increase, M increase. Or when M increase, the modulation index increase, the efficiency increases. So example, okay, you can do this exercise, you can do this on your own. Okay. AM power efficiency from the previous example, what percentage of the total power was dedicated to transmitting the carrier? Okay. So power LSB 5.4, power carrier 30 watt, and USB 5.4. So, okay. Is any information conveyed by a carrier itself? So, is the information carried by the carrier? No. How could we maximize the power in the sideband? So, the problem is there is no information in the carrier, but it carry large amount of power. So this is like waste, not efficient. Okay, so sideband power is maximized by setting M equal to 1. So when we have motion index equal to 1, so sideband power is at maximum. At M square over 4 PC. For M equal to 1, what percentage of the total power is dedicated to the sideband? Okay, this one you need to calculate. Okay, AM power efficiency at maximum modulation, the sideband power is almost 33% of the total transmitted power. So this is the graph. percentage modulation over percentage of total power. So this is the power in sideband. This is the percentage modulation. So at 100% percentage modulation or motion index equal to 1, the power in the sideband only up to 33%. Okay, 33%. At maximum modulations, motion index equal to 100%, or percentage motion 100%, the power in sideband is only 33%. 33% here. The problem is this signal carries its information in the sideband. So basically, the rest of the power is not efficient. It's not being used properly. So 2/3 of the power is waste in the carrier. Further, 100% modulation only occurs at peak in the modulating signal. Thus, the average sideband power is considerably worse than the ideal. Because it's quite difficult to get the power at peak. So basically, theoretical, you got 33% efficiency, but in practical, you might get lower than this value. Okay. Improving on AM. So what we can do, besides the 7 power loss due to the carrier, the sidebands contain redundant information. Okay, so basically, because upper sideband and lower sideband in AM signal carries the same power, it also meaning that it carry same information. Okay, so the sideband contain redundant, so same information, redundant. To maximize the efficiency of AM, we need to, one is we need to suppress the carrier, we need to remove the carrier because the carrier doesn't bring any information. So we don't really need that. Second, eliminate one of the sideband. Okay, if you want to improve further, instead after remove the carrier, we need to eliminate or remove one of the sideband. Okay, upper and lower sidebands contain the same information, so we just need only one. Okay, so this example. So that's why the disadvantage of AM modulation. But why AM is still being widely used? First, AM is still widely being used because it is simple and effective. It is simple and effective. Okay, so this is the technology that still be using AM modulation techniques. AM broadcast radio, CB radio, TV, traffic control, remote control, and so on and so forth. Okay. Next, types of AM. There are a few types of AM. In order to improve the signal for AM, improve the efficiency of the AM signal. The first is double sideband full carrier. This is the default, the common AM, the basic AM. We call it double sideband full carrier. The signal has double sideband, upper and lower, and also carrier, full carrier. This is what we have discussed before. The second type is double sideband suppressed carrier, DSB-SC. Double sideband the remove carrier. Contains only upper sideband and lower sideband. The circuit that produces double sideband DSB-SC is a balance modulator. So we use balance modulator to remove the carrier. But upper and lower sideband is still remain. The third types, the third type is single sideband, SSB. In this modulation technique, only half of the signal of the double sideband, a suppressed carrier is used. So from this signal, so we remove another sideband, we have single sideband, SSB. Contain either lower sideband or upper sideband. Produce efficient system in terms of power consumption and bandwidth. So in this single sideband AM signal, we have increased the efficiency because the transmitter do not need to transmit the carrier or one of the sideband. We just send only single sideband through the transmitter. So there is a good in terms of power consumption, meaning that all the power being used is used for transmission of the information in one of those sideband. Okay. Type number 4 is vestigial sideband. This is a modification of the single sideband to ease the generation and reception of the signal. So you can, if you want to know further about this, you can look for the information on your own. Okay, exercise S1, exercise 2. Okay, try to do this exercise. If I have time, I will do some exercise in Kalam for this question. Okay. If you don't have any question, then that's all. That's all for now. Thank you very much for your patience, and that's all. Okay. Bye bye. Assalamualaikum. See you in the next class.